First couple sections of which will be on exam 2 this summer. And the first part is equations. Now, some of you have probably seen equations before and you may know all these terms, but again, we're going to make sure everybody is on the same page. Now, this arrow means that a reaction occurs. And when we start doing math with equations and reactions, etc., we're going to kind of treat that as an equal sign. It is not an equal sign. Don't write it as an equal sign, but you can line them up as an equal, because basically what it's saying is the reactants are going to the products. And remember about the law of conservation of matter, where atoms are strictly rearranged. You can't create more, nor can you get rid of them. So when we balance them, we've got to keep up with the numbers. Okay, delta is usually placed on top, and it means heat is needed for the reaction to occur. Okay, S means that the species is in solid form. L means that it's in liquid form. And G means it's in gas or vapor form. And aqueous, AQ means aqueous, which we'll get into in chapter 4 in a lot more detail, but that means dissolved in water. And hence the aqueous water. Okay, now at the bottom you'll see this little note, cannot use grams directly when working with equations. I'm going to keep putting that up there because that's critical, and right now we don't need it, but I want you to keep it in the back of your minds. So we're still talking about the equations, and when we talk about the equations, we're talking about the reactants and the products. Okay, so if you'll notice, up here on top, you have a catalyst, heat. HV is light, electricity, etc. Anything that might be needed to make the reaction proceed is the catalyst. It goes on the arrow, and it's not a reactant, nor is it a product. And especially since when I'm standing in front of a group, I have a problem with left and right, I'm going to use reactants and products for most things. Now, if you look at it, we have a 2 here, and a 1 is understood here. And it's understood because you can't have a 0. If you had a 0, it wouldn't be there. So these are the species you change when balancing. Okay. The subscripts, on the other hand, are associated with the compound. You don't touch those when balancing them, because if you do, then that changes the compound. Okay. So, for example, CO, if you need 2 oxygens, is absolutely not the same as CO2. You can't do that. You're only allowed to change coefficients out front, not subscripts. Okay, and remember we saw the physical states previously, so we're good on those. Now, there are rules to balancing equations. You can use them, keep it handy, the list, when you first start balancing. After that, it's really easy. Okay, you're going to, first rule is vary the coefficients only, never the subscripts. Remember, that changes the compound. We need to keep the coefficients as whole numbers. I will show you how to balance one that's easier to balance as a fraction initially, and then you just get rid of it. But most of them don't do that. Just every now and then one does. Coefficients need to be in the lowest ratio possible. So if you had 2 plus 4 is 2 plus 6, then that's not the lowest ratio. You would need to divide everything by 2, so you get 1 plus 2, 1, and 3. Okay, that's what we're talking about there. And again, I didn't put in compounds, but I wanted to show you. Now, in general, it is easier to balance if you balance when hydrogen and oxygen last in that order. What that means is balance all the species first, then balance hydrogen, and then oftentimes oxygen at that point will either be balanced or easy to balance. If you try to balance oxygen first, it tends to mess up all your other elements in terms of species. Okay. A trick, and some people like it to use it and some people don't. It just makes it harder if you don't. But if a polyatomic ion appears but doesn't change, it can be treated as a single unit. So you can call it Fred, George, Harry, whatever you want, red ball, whatever. But if you have 3 on one side, you have 3 on the other. And this only works if it doesn't change. And again, I'll show you an example of where it changes and where it doesn't change. Okay? So the first thing we're going to do is balance the following equations. Now, remember the number of each atom on the reactant side has to equal the number of atoms on the product side. So there are people who make tables, and you can do that, and that is perfectly acceptable. However, I want to warn you, it is a crutch. It takes a lot of time, and most people can keep up with counting in their head, or you write it up underneath, and that's fine too. I strongly recommend not to write anything on top of an equation. I'll explain that later as we get into balancing precipitation reactions, because that may change the species. So bottom line is that you need to keep up with the numbers. So it's relatively straightforward. Here we're going to work. I like to work left to right so that I don't miss one. So here's sodium. And again, you shouldn't have any problem because everything that's on the reactant side should be on the product side. So according to this, I have 2 sodiums. So that means I have to have 2 sodiums here. Now remember, if you have 2 NaBr, what it acts like, there are no parentheses there. Let me go ahead and get rid of the parentheses. But it acts like as if you had parentheses, 2x plus y, you distribute. So this means that you have 2 sodiums and 2 bromines. Okay, now they wouldn't be that elemental form, but I just want you to count right now. So we have 2 here. So we've done that. Now we'll move to the sulfurs. We have 1 sulfur over here. We have 1 sulfur over here, so we're good on that one. So then we move on. We're going to skip hydrogen and go to bromine. Over here we have 1 bromine on the reactant side. We now have 2 on the product, so we need 2 over here. We've balanced everything but the hydrogens, so now we're going to go back to it. We have 2 hydrogens here, we have 2 hydrogens there. Voila, we are balanced. The hydrogens took care of themselves. Okay? And again, if balancing the hydrogens probably wouldn't have hurt anything on this one. Sometimes it does, sometimes it doesn't, but it just makes life easier if you follow the rules. Okay, so then on the next one, we've got potassium. We've got 1 here and we've got 3 here. So we're going to need 3 potassiums here. We're going to skip the oxygens and the hydrogens. Again, we're going to skip the hydrogens, so we're going to deal with phosphate here, and lo and behold, we have phosphate the same on both sides. So we're going to leave those as is, no problem. Now we go back to the hydrogens. So if we look, we have 3 hydrogens here and 3 hydrogens here. So we have 6 hydrogens on this side. Over here, we have 2 hydrogens. So in order to get 6, we need to multiply it by 3. So we'll put 3 hydrogens right there. Okay? And I'm going to change colors to make this easier, I think. So if I look at the oxygens here, I have 3 oxygens here. Can't count any oxygens here because that's in the phosphate and we're not changing. So over here, we now have 3 oxygens, so we are balanced. So the oxygen took care of itself. Okay? So we'll move on to the next one. We'll again start with potassium. And we have 2 potassiums and 2 potassiums, so we're good there. And I'm going to try this. I don't know if this is a good idea or not. S2O3 is here, but is S4O6, so that's changing, so we can't treat it as an entity. So this one has, if we look at it, 2 sulfurs. This one has 4 sulfurs. So we're going to need to multiply this by 2. Well, having done that, we've got to go back and look at the calcium, because now we have 4 potassiums. So we have 2 potassiums here, so this needs to be multiplied by 2. No, it doesn't. Wait a minute. I can't do math because I got 2 here and I've got 1 here. That's what happens. So it wasn't balanced before either. So we kind of lucked out on this one. So if we look at it, let me give you a hint. If you multiply an odd number by an even number, so 2 times or 3 times 2, you'll always get an even. Okay? But if you're adding an odd plus an even, will always give you an odd. So if you have an even number on one side over here, we always have to end up, if you have an even number on one side, you have to end up with an even number on the other side. So the easiest way to fix that is to multiply an odd to get an even. Okay, so in this case, if we look at it, we've got 4 potassiums here, 2 potassiums here, and only 1 here. So if we multiply this by 2, we're up to 2. So 2 plus 2 on this side is 4 potassiums. So we have achieved 4 potassiums over here and 4 potassiums on the reactant side. So we're good there. Let's double check our sulfurs, since I managed to mess that up. So now I have 4 sulfurs over here. I still have 4 sulfurs over here. So life is good. We're ignoring the oxygen. And we'll move on to the iodide. So the iodide has 2 iodides here and 2 iodides here. So we're good. We don't have to do anything else. Now the last one is we have 6 oxygens over here. We have 6 oxygens over here. So guess what? We're balanced. So this one was a little bit harder because the sulfurs changed, but it really wasn't that bad. So let's look again over here. So on problem D, we have silicon. And we have one of these over here. And this time I'm going to double check it. Here I have 1. So we're good. Okay, we're skipping the oxygen. We're going to move to the bromine. Here we have 1 bromine. Here we have 2 bromines. So here we need to put a 2 there. Okay. So we move to the fluoride. So now 2 times 3 is we have 6 fluorides here, but wait a minute, we have 4 fluorides here. All right, so that's going to make things a little bit on the crazy side for us. So let's go back and rethink. So when we go back to rethink, so we don't lose our minds, we're going to go ahead and erase anything we've got in there. And so we now are aware that our fluorides are our problem child. So once we've done that, we're back to 3 fluorides here and 4 here. The smallest number that 3 and 4 can go into is 12. So let's even that out. So that means this gets multiplied by 4 and this one gets multiplied by 3. So then our fluorides balance. Now we've just messed up silicon and bromine. So let's go back to silicon. Now I've moved to 3 silicons And I still have 1 over here, so I'm going to need a 3 here, so I'll add the 3 there. So now my silicons are balanced, my fluorides are balanced, and I have to go back and deal with the bromines. So now I have multiplied this, and I have 4 bromines here. I still have 2 here, so I'll multiply by 2, so I'm good to go there. All right, now that leaves us with just the oxygen to balance. So now I have 2 times 3, which is 6 oxygens here. And I have 2 oxygens here, so I'm going to need to multiply this one by 3. Okay. Now, one other double check. Remember the rules? It said that you have to have the lowest ratio possible. So if you filled in every single line, you need to go back and double check and make sure A, it's a whole number, and B, it's the lowest ratio. So if we look at it, we have 3, 4, 3, 2, 3. There is nothing that will go into all of them, so that is the lowest ratio possible. So that one stands. Okay, so let's move on to equation E. So first things first, we have 1 lead here. We have 1 lead here, so we're good. We have a nitrate here, and we have nitrate here. It didn't change, so we can leave it alone, but we can treat it as an entity. We have 4 here. We have 1 here, so we need to multiply this one by 4. All right, so we've done the leads and the nitrate. Let's do the sodium. So here we have 1. Here we have 4 because we multiply it by there. So we need to multiply this one by 4 here. The last one we have to look at is chlorine. We have 4 chlorides here, and we have 4 chlorides there. So we're balanced. So we have just balanced this equation. Okay. All right, now the last one is a combustion analysis. More about that in just a minute, but anything that gives you CO2 and water is combustion. Reacts with oxygen here. This is an organic compound. You know that because it only has carbon and hydrogen in it. Can't have carbon, hydrogen in a third element or fourth element, but it starts with carbon. So oftentimes these are a little crazy to balance, but we're going to try to balance it anyway. So here we go. We have 2 carbons here. So we need we have 1 carbon here, so we need to multiply this by 2. Okay. Now all we have is hydrogen and carbon left. So we have 6 hydrogens here. We have 2 hydrogens here, so we're going to multiply it by 3, which gives us 6. That brings us to the oxygens. We have 4 oxygens here, and we have 3 oxygens here. So we have a total 7 oxygens. So if we look at it, what would we need to multiply 2 by to get 7? So if we multiply 2 by 7 halves, then that would give us 7, right? So we would put in 7 halves. Now, you could go back and you could multiply the first species by 2. But at this point in time, we got it balanced. But one of the rules was we had to have whole numbers. So just like math, if you have a fraction and you're trying to get rid of it, then you multiply everything by 2. So we're going to multiply everything by 2. So this goes to 2. This goes to 7. This goes to 4. And this goes to 6. Now, if I was working this for a test, I would erase those and write it down in the spaces. But since this is an explanation and I'm trying to show you how it works, then we're good to go. And then again, just so we see, we've got 2 plus 7, 4 plus 6. And again, the rule applies as if I've got numbers in each block. Let's make sure I can't be reduced. We can't reduce a 7. It doesn't go into anything with 2, 4, and 6 evenly. So those are the lowest ratios possible. So we balanced them. So even though we were able to balance it using a fraction, And again, some people don't like fractions, so you can just go back and double the original compound, C2H6. You're good to go, and you can balance it either way. Again, whichever one makes you happy. All right, so now we've done nomenclature at the end of the previous chapter. We've now learned to balance equations. So we're going to work on writing out equations. Now, the trick to this is you have to apply both rules. So we say the reaction is solid sodium carbonate. Okay, well, carbonate is, CO3 2 minus, sodium is 1 plus. So in order to find a balanced compound, we have sodium 2 carbonate. We're told it's a solid, so we put in there. With nitric acid, well, nitric acid is nitrate, so it's the hydrogen nitrate. And if it's an acid, we know that it goes in as aqueous. Now notice as I'm writing this, I'm leaving space in front of each compound so that we can go back and balance it. We're going to yield, that means that's our arrow. Water, and I didn't specify what that was, so you can do it whatever. I'm going to do liquid. Carbon dioxide gas, plus aqueous sodium nitrate. Now, the other thing I needed to have done was write smaller, which I didn't do, and start to the left. Again, if I was doing this on a test, I would have written smaller and started to the left. And if not, I would have erased it and redone it. As long as it's legible, life's good. All right, so now I have all my compounds. I have all my states. And now I just need to balance it. So I have 2 sodiums here. So let's put a 2 up front here. The carbonate doesn't reappear, so we have to treat it separately. So I have 1 carbon, so I'm good there. The nitrate stays together, so I have 1 nitrate here, 1 nitrate there. So now I have to do the hydrogens. I have 1 hydrogen here, I have 2 hydrogens here, so I need 2 of these. Oh yeah, I missed the nitrate because I should have caught it there, but again, it's a double check, so it'll catch it. So I've got my hydrogens, and I need my oxygen, so I have 3 here. I have 1 here and 2 here, so I have 3. So I'm going to double check it since I kind of messed it up. 2 sodiums, 1 carbon, 3 oxygens, 3 oxygens, 2 hydrogens, 2 nitrates, life is good. Okay, so this one is balanced. So let's move on to the next one. Solid iodide monobromide. Okay, so iodide monobromide, solid, reacts with liquid ammonia. And ammonia is NH3, liquid. To yield, there's the arrow, nitrogen triiodide, that's 3, solid, plus ammonium bromide. And since both ammonium and bromide are 1 plus and 1 minus respectively, it's 1 to 1. And that was solid. Okay, so solid iodide monobromide reacts with ammonia liquid to yield nitrogen triiodide solid and ammonium bromide solid. So I've got my species. Now I need to balance it. And again, this is where partial credit builds in. If you're asked to do this, then you also need to submit the work, because if you accidentally mess up a species, for example, instead of doing Ni3, you did N3I, and I'm not writing it down so you don't copy that. Then when you go to balance it, it'll change the balancing so that I can see exactly how and why it got messed up. Okay, so I have 1 iodide here, I have 3 here, so I'm going to put a 3 here. I have 3 bromides on the reactant side, so I'm going to need 3 on the product side. Now, the nitrogen is not the same species, so we're going to have to do it separately. So I have 1 nitrogen here. I have 1 plus 3, which is 4. So let's try 4 here. That gives me 12 hydrogens. That gives me 12 hydrogens. I'm good. So now I have written my equation species, and then I have balanced it. And remember, if you mess up the species, it messes up the balancing, which is why partial credit is your friend. Okay, so the reaction of aqueous stannous acetate with hydrofluoric acid results in stannous fluoride and aqueous acetic acid. Okay, so stannous, if you remember, is the lower 10 value, and your options are 2 plus and 4 plus, so that's 10 plus. And acetate, remember, is C2H3O2 minus. Hydrofluoric acid is HF, and since it's an acid, it's aqueous. So when we combine these, we're going to need 2 acetates, so that's 10 C2H3O2 2. And because it's polyatomic, go in parentheses. So that's our reactant. So we'll go ahead and write that in. 10 acetate C2H3O2 2. And that was aqueous. Plus HF. And again, I'm leaving space. Acid. So that's aqueous. Yields stannous fluoride. And remember, fluoride is F minus. So we're still 2 F2 solid plus aqueous acetic acid, which is acetate with the proton on it. Okay, so now let's look at balancing. We have 110, 110. We have 2 acetates, so we'll need 2 acetates. We have 2 fluorides, so we need 2 fluorides there. Now we have 2 hydrogens, 2 hydrogens. So we have set this up and we have balanced it. So we're good to go on this problem. Okay. Now that brings us to the evidence of a chemical reaction. If you're doing a lab, how do you tell whether you have a physical change or a chemical change? You usually look for the evidence of a new substance. A lot of ones are visual clues, most of which are permanent. Color change, precipitate formation, and a precipitate, and we'll get to this in a lot more detail in 4 as we work these, forms a solid. So a precipitate is abbreviated PPT. Gas bubbles, and the trick to gas bubbles is sometimes they form real quickly and then they go away, so you don't see them per se if you're not paying attention. So as you're running a chemical reaction, you need to pay attention because it may form, and if you're not paying attention, then you didn't notice that the gas bubbles form, because they may form and then once the reaction is complete at that part, they stop. Large energy changes, and sometimes if it's in a test tube, you place your hand around the test tube. Now be very careful when you do this, or you can just touch it. Touching it is better in some cases. If it's a small change, your hand around it is going to be fine. If it's a large change, you don't want to hold on to it, so be very careful. A lot of times the easiest thing is to hold it at the top and then touch it or place your hand around it quickly so that you can let go without dropping it and shattering it. Another one, and these are one of my favorite things to play with, is glow sticks, and they emit light. And if you've ever paid any attention to your glow sticks, you can get them at the dollar store. The inside are little metal capsules basically, and you have to pop all of them to get it all glowing, which is also why if you shake it, it glows faster. But if you're careful, you can pop one, let it glow, and then when it dies, you can pop another one just for fun and entertainment watching chemical reactions. Other clues, sometimes you have a new odor, sometimes it smells good, and sometimes it stinks. Whooshing sound from a tube. If the gases form very, very quickly, then oftentimes it goes quickly and you just hear a sound. Okay. And in other cases, you can have a permanent new state. The one that comes to mind immediately is when you take an epoxy compound. My father loved epoxies. And where you mix tube A with tube B. Tube A is fine, it's a liquid. Tube B is fine, it's a liquid. But the minute you start mixing A and B, it kind of gets thicker, and then when it hardens, it's hardened. So if you accidentally mix A and B before you're ready, your epoxy is toast. So you cannot use it because it's already solidified. All right. Now, we can classify different reactions as chemical reactions, and there are several types of chemical reactions. We have 7 main ones. The first one is a double displacement or metathesis reaction. Precipitation reactions fall into this. Acid-base fall into this. Anything that basically changes partners. And it's both. And as I said, we'll work these before. So if you have A, B plus C, D, when it rearranges, you're going to have A with D and C with B. And notice the cation still has to be listed first. So you're going to change partners in a double displacement. An acid base is a neutralization reaction. This is where you're going to form a salt. And remember, salt is an ionic compound and water. We'll look at each of these individually. But an oxidation reduction reaction is known as a redox reaction, and is where oxidation numbers vary. Again, look at that. Combination, you're going to combine species so you have fewer products. Decomposition means that you have more products than you do reactants. Combustion reaction is going to react with oxygen to form CO2 and water. And then a single replacement is like a double displacement, but you have only one species changing. So if you had A plus CD, then you'd end up with C plus AD. So you change partners with only one species. And again, I'm going to show you examples of each one of these. But you will be asked to classify equations this way. Okay? So, first one we talked about was the addition or a combination reaction, and you have more reactants going to fewer products. And it may be, in this case, we have 2 reactants going to 1 product. We may have 3 reactants going to 2 products. We just have less. So more on this side and less on this side. And when I say more and less, I'm not talking about the atoms. The atoms have to count. I'm talking about the number of compounds. Okay? Because your atoms have to stay the same. Another one is decomposition. Combination is combining things. Decomposition has more products. It's the opposite of an addition or combination than reactants. And in this case, this one's got heat. Most of the time, decompositions, not always, require, this is electricity, require something to get them started. And if you'll notice, you'll have less on the reactant side and you'll have more species on the product side. Number of species. Okay, and again, and you're like, wait, we have 1 and 2 here. Yep. but we'll still be a balanced equation. Okay, so you may be asked to classify equations as we go. I forgot to re-put in the balancing, but I'm going to go ahead and add a slide and just list them so that if you go back and look at the balancing equations, you can classify them. And I don't want to go back and write it in there because that may confuse you with the first part. So we had A, B, C, D, E, and F. Now, the beauty of equation classification is that a lot of them are more than one. Most addition and decompositions are also redox, and we haven't done those yet. So I'm going to list it, but later when we do redox, we'll classify them again. But right now, I want you to look at them. A is a double displacement, which is also known as a metathesis reaction. And metathesis is the old terminology. And since I'm old, in case y'all didn't figure that out, back in the dark ages when I took chemistry, we didn't use double displacement, we used metathesis. So you'll hear me use them interchangeably. That also happens to be a precipitation reaction because it forms a salt. The sodium bromide is a salt. B is forming a salt and water, so it is an acid-base reaction, but it's also a double displacement. Okay. 3 is going to be interesting. It's going to be a redox. We haven't done oxidation reduction on it yet, but when we do that, you can come back and look at it and go, oh yeah, it's redox. Primarily, I want you to worry about the metathesis and the oxidation, not everything but the redox. Okay. D is silicon dioxide with bromine trifluoride going to silicon tetrafluoride and bromine and oxygen. So it is a decomposition because there are more products than there are reactants. And it's also a redox. And even though we haven't done the oxidation numbers, we did them actually for naming, but we haven't done them in equations. You can look at it and see that you have bromine on one side that's not elemental and one that is elemental. That's an immediate sign that that's a redox. If you have the form on one side that's elemental and the other side that's not, then you're not. Then you're definitely a redox. E, you're doing a metathesis or a double displacement. And that actually should produce a solid, so it should be a precipitation reaction, but I didn't write one, so we're good there. F is a combustion because you added oxygen and you got CO2 and water. And because oxygen is elemental on one side and not on the other, it's a redox. So we've balanced these equations, and I really want you to worry primarily about these, not the decomposition, the redoxes yet, okay? And you should be able to calculate that.